Hello class, this is the last example on the proof of mathematical induction. This last one's a little bit trickier in that it's a multiplication instead of a summation. So let's take a look at how we do this. I've already written up a few bits just to save us some time, but the method still kind of continues as per usual. So when we let n equal 1, it'll become 1 plus 1 equals, because we're only taking the first term, 1 plus 1 is equal to 2 to the power of 1 times the first term here as well, times 1. This is 2 is equal to 2. So this is true for n is equal to 1. Now, I'm going to show you for n equals 2. You don't have to do this, but it'll make, I'm showing you this to make it a little bit easier to understand the meaning of this expression for later on. So if it's n is equal to 2, we get 2 plus 1 times 2 plus 2, we stop there, is equal to 2 to the power of 2 times the first two terms in that bracket. So 1 times 3. This is nice and simple. This is 3. That's going to be 3, and that's going to be 4. 3 times 4 is 12. 2 to the power of 2 is 4. 1 times 3 is 3. This also gives us, goodness, I even said it, that's 12. And this right hand side is also 12. So this is also true for n is equal to 2. Now remember, you don't have to do that. It's just I'm demonstrating to you how we would use it for this application here. Now we assume it true for n is equal to k for any integer. K is greater than 1. Once again, to save us some time, make this blue, and instead of n, we get k. So let's do the left hand side first. K, 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 and the right hand side, 2 to the power of k, 2k minus 1. So we're going to prove this to be true. Sorry, we're going to assume that this is true. But what we need to prove is for n is equal to k plus 1. But now look very carefully when we substitute it. If we substitute k plus 1 here, this group will become k plus 2. If we substitute k plus 1 here, we get k plus 1 plus 2. It'll become k plus 3. If we continue that pattern, we get this. So it becomes k plus 2, k plus 3, k plus 4, and so on, all the way up until 2 times k plus 1. The right hand side stays as normal. 2k becomes 2k plus 1. Inside this bracket stays the same, but this expression at the end will change. It'll become 2k plus 1, 1 times 3 times 5 times dot dot dot. Now if we expand this, we get 2 times k. 2 times 2 is 2, minus 1 is positive 1. So it becomes plus 1, like that. And this is what we need to prove. This expression is equal to this expression. Now let's take a look at the left hand side. We have k plus 2, k plus 3 times dot dot dot. And as per usual, we always have that extra term right before k plus 1. we have that 2k times 2 times k plus 1. Now, normally we would do a substitution, but take a look. We can't substitute it because this expression begins on k plus 2, whereas this begins on k plus 1. So we can't do a direct substitution of this equaling this and substituting it here. However, since we're assuming this statement to be true, we can manipulate it a little bit to become this: k plus 2, k plus 3 times dot 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 2k. It's going to be the exact same thing. Let's get rid of that word 4. Except in order for the left hand side, for this, notice how I've removed k plus 1. What I've actually done is I've divided it out like so. Now the expression is exactly as we want it. That expression is beginning on k plus 2 all the way up until 2k, which is matching exactly as we want. So we're going to substitute that. We're going to substitute this entire expression in. This is going to multiply by this term here. So just being very careful now. This expression is equal to this expression. And I've substituted just that here. We're still left with 2 times k plus 1. Now from here, since everything is a multiplication, these two cancel. And the base of 2k times 2 are the same. So when the bases are the same, the indices add. So we're left with 2k plus 1 outside of 1 times 3 times 5 all the way up until 2k minus 1. However, if you take a look, this expression, well, I can't think of any way to simplify it any further, but this expression is not equal to what we needed, because we have 2k plus 1, but this is 2k minus 1. So we can say that this is not equal to the right hand side. Now this is the only example that I've done to show this, because sometimes it's actually not a true statement. So in cases such as this, we simply write the exact same thing. The statement is not true for all n is greater than or equal to 1, since it is not true for n is equal to k plus 1. And that's it. So it's sometimes the case that no matter how much you work the problem, it just doesn't seem to be the case, but these are rather rare. And yeah, that concludes all the examples we have for proof by mathematical induction. Hope to see you in the next video. Best of luck.